Namaste students, welcome back to Rama Teaches You. Today we are going to do class IB Physics. IB Physics class 11. Okay. And the name of the chapter is Electric and Magnetic Fields, and we are going to do the fourth part of electric and magnetic fields. So in today's class, we are going to do magnetic field patterns due to a current in a long straight wire. We sorry. We know that the magnetic field is produced when a charge is moved, right? Whenever a charge is moved, we experience a magnetic field. So the magnetic field pattern due to a current in a straight long wire is a circular pattern centered on the wire. This seems odd to anyone previously used to bar magnet patterns. Observations using plotting compasses show that the direction of field depends on the direction of current. Now, this is how it looks like. Okay, you have a straight conductor like this, and then I'm going to place. Okay, so basically, this is how if a current is flowing like this, the magnetic field around the conductor will be in the shape of a cylinder having a certain amount of radius r. Okay, r depends on the distance of the magnetic compass from the straight wire. Okay, so this is what basically is meant when they say this magnetic field. Okay, due to a straight conductor, it's in the form of a cylinder. According to the using the conventional current, that is the direction that positive charge drifts in the wire, see page 303, the relationship between the current and the magnetic field obeys the right hand corkscrew rule. For example, let us imagine that this cap is the direction of the current. Okay, if I hold the cap like this, the thumb is pointing to the direction of current, right? So the fingers that are curling like this will give us the direction of the magnetic field produced by this wire. So what do you observe? You observe that there is like a cylindrical magnetic field around this conductor carrying current. Am I right? Okay. And now keep your pen in your hand. Keep your pen in your hand and see what happens. Now, when the thumb is pointing upwards, the magnetic field is in the direction anti-clockwise direction. Am I right? You have to use your right hand. Okay. But when I basically put the thumb downwards, if the current is moving downwards, then what happens? The magnetic field is in the clockwise direction. Okay. Next. To remember this, hold your hand right with fingers curled into the palm and the thumb extended away from the finger. The thumb represents the direction of the conventional current. Okay, the thumb represents the direction of the conventional current, and the fingers represent the direction of the field. Another way to think of the current field relationship is in terms of screwdriver being used to insert a screw. The screwdriver inserts a right hand screw by turning clockwise to drive the screw forwards. The direction in which the imaginary screw moves is that conventional current, and the direction in which the screwdriver turns is the field. You just have to remember this, nothing else. Okay, this thumb, you curl your fingers like this. Okay, you curl your fingers, the direction of the curl represents the direction of the magnetic field in which it's going. Okay, now remember that the rule works for conventional current. The further the pattern is from the wire itself, the greater the separation of the field lines. This is telling us that the magnetic field strength decreases as the distance between the wire increases. Okay, so if this is a wire, the magnetic field will keep on decreasing as I increase the distance between the wire and the field and this thing, okay, and my hand. So my magnetic field is decreasing like this. Okay, now due to the current in a circular coil, the magnetic field due to a coil is shown in figure 36. A coil is a circular winding of wire with thickness of the coil much less than its diameter. Okay, you have basically coiled the wire. Instead of having a straight wire, now you are having a circular wire with many loops. To understand how the magnetic field pattern arises, you need to imagine a long straight wire being formed into one turn coil shape. As it does so, it carries the circular field with it so that the circular field bends round. Figure 36 shows this. The field lines run along the center of the coil and then around the outside. The pattern is identical to the bar magnet pattern, so that we can assign north seeking and south seeking poles to the coil. I'll show you how it looks like. So just draw two circles like this. Okay. Draw a clockwise current flowing in this coil and draw an anti-clockwise current flowing in this coil. Okay. Now just draw this line, and can you see two letters here? This is S and this is N, right? So basically, if in a coil the current is in the anti-clockwise direction, then it will represent a north pole, and if it's in a clockwise direction, it will represent a south pole. Now, what is the major difference between a magnet and an electric charge? A magnet will always have two poles, always. Okay, you cannot have an isolated monopole. Okay, that was the beginning of our chapter, right? You cannot have a monopole, but for a charge, you can have an isolated charge. Okay, now, Akshay, if you have a coil, if you have a coil like this, then if I look the coil from one direction, what will I observe? I will observe that it is going in the clockwise direction. Okay, observe my hand. Observe my hand. Okay, now if I'm looking it from here, I can see that it is in the clockwise direction. But if I look it from here, what do I observe? From the back, I observe that it is in the clockwise direction, anti-clockwise direction. Okay, so an observer from this side will observe a clockwise direction current flowing, but an observer from this side will observe an anti-clockwise direction. So a looped coil will have one side to be the south pole and the other side automatically becomes the north pole. Understood? Okay, so this is how the shape looks like. Look at this. So you know that the magnetic field lines enter the south pole and exit the north pole. They enter the south pole and exit the north pole, right? So look at this. So the field lines are going like this. So they are exiting the north pole and entering the south pole, just like that of a bar magnet. Understood? So we can consider the coiled loop to be that of a bar magnet. Understood? Okay, let's move on. So the field lines run along the center of the coil and then around it. The pattern is identical to a bar magnet, so that we can assign north seeking and south seeking poles to the coil. The easy way to remember is to use N and S to show north seeking and south seeking poles. The arrows of N and S show that the current direction when looking into the coil from outside. When the conventional current is anti-clockwise, as you look into the coil, then the end is north seeking from behind. Okay, now, but if you look from the front, what do you observe? You observe a clockwise direction current. So that automatically becomes the south pole. Okay, now, how do you increase the strength of the magnetic field produced by a coil? You can only do that by using what? By using either more loops or by physically increasing the current that is flowing in the coil. These are the two ways by which you can increase the current. Understood? Okay. Due to current in the air core solenoid. Now, we have learned about the straight wire, we have learned about the loop, and now the third and the final part is a solenoid. Okay. So, a solenoid is a form of coil where the coil length is much greater than the diameter. The magnetic field pattern is similar to that of a coil and it arises in similar ways. Two adjacent turns of wire in the solenoid are as shown. Okay, so Drupad, sorry, Akshay, this the solenoid looks like this. Have you ever seen those pens that are clicky pens? They have a spring. Now imagine if the spring does not have any space between the coils. Okay, if it does not have that much space between the coils, you will get a solenoid. Okay, when current in the wire, with current in the wire, a circular field is set up in the wire. The familiar circular field adds together with identical fields neighboring turns in the solenoid, from neighboring turns in the solenoid. Figure 335 shows this. Look closely at what happens to the individual wires. The black lines show the field near the wire. The blue lines show how the field begins to combine. Now look at this. See, this is how the field actually goes. You have a solenoid here. Okay, the magnetic pattern of a coil or a solenoid is formed from the addition of magnetic patterns from many parallel straight wound wires together. Outside a solenoid, the magnetic field pattern resembles that of a bar magnet, but without the poles. Okay, now it actually looks like this. Okay, if you have a solenoid like this, okay, so just imagine you have an imaginary sheet of paper like this. Okay, so basically, if you place if this is the imaginary paper, okay, I am basically going to allow the wires to go through this imaginary paper. One, two, three, four, right? So basically, every single wire is going through this imaginary paper, crossing through this imaginary paper. Okay, so what happens here? It is basically what is happening here is that the number of current coils as they increase, each coil is producing its own magnetic field. One second. So the wires are entering inside the uh, imaginary piece of paper. So each and every single coil is producing its own magnetic field. That's what we learned, right? A coil produces a magnetic field like the ones here, right? So you have multiple coils going through the same imaginary paper, okay, and that imaginary paper's magnetic field starts to add up. Okay, that's how you get a solenoid. Okay, now I don't think you have derivations here. In India, we actually go through the derivations of each and every single the coil, the straight wire, the solenoid. Okay, so like for a solenoid, the magnetic field is given as mu naught Ni. Okay, I don't think you have that. Figure 37b gives an overall view of the magnetic field once it's built. Remember that the field is only shown in one plane and in three dimensions. It rotates through 360 degrees above the axis of the plane. This appearance of the north-seeking and the south-seeking poles of a solenoid obey the same rule as that for a coil. Okay, so this is how the magnetic field lines look like. Okay, so this is how they will look like. Yeah. So inside the solenoid, they are uniform. Okay, they are uniform, and as they go out, they curl like this. So this is the north pole, and this is the south pole. This is how a solenoid would look like. Understood? This is a spring. In the spring, the current is flowing. Okay. In the spring, the current is flowing and it is behaving as a bar magnet. So there are a lot of equipments that we use in everyday life that requires a uniform magnetic field. Okay. A uniform magnetic field is required for such operations. So to get a uniform magnetic field, you can use inside that of a solenoid. Inside a solenoid, you have uniform magnetic field. If you place an object inside the solenoid, it will experience a uniform magnetic field. Understood? Okay. The strength of the wire magnetic field in a solenoid can be increased by increasing the current in the wire, increasing the number of turns per unit length of the solenoid, adding an iron core inside the solenoid. How does an iron core work? An iron core is a paramagnet. Okay, it is a paramagnet. So basically, if you place it in a magnetic field, it will force the magnetic field lines to go through it. Therefore, what will happen? The strength of the magnetic field inside the iron will increase. Therefore, the whole solenoid plus the magnet, whereas plus the iron, will behave as a strong magnet. That is what we use for electromagnets. You have seen electromagnets, right? Those devices that basically are used to lift cars and all. Yeah, yeah, exactly. They are used in the scrapyard. They're basically built by using solenoids only. Solenoids and a strong core. Okay, you have a really strong core, iron core. Okay, and every single time he passes current through those coils, the whole that block becomes magnetic. So once it becomes magnetic, it is able to lift the wire, lift the car. But as soon as the current stops flowing through the what do you say, through the wires, then the whole magnetic field will get disappeared. It will get erased. Understood? That's how it works. Clear? Four long straight wires are placed perpendicular to the plane of paper at the edges of a square. The same current is in each wire in the direction shown in the diagram. Deduce the direction of the magnetic field at point P in the center of the square. Sorry. Okay. So four straight wires are placed perpendicular to the plane at the edges of a square. The same current is in each wire. Okay, deduce the direction. Okay, so if the current is going inside here, okay, then the magnetic field will be like this. Okay, at this particular point, the magnetic field will be like this, and due to this, at this point, it will be like this. At look at this. See, but all I'm doing is I'm using my thumb. Oh, sorry. Dot means that the current is coming out, right? So let's put the thumb in the direction of the dot. Okay, it is coming out. Now what happens here? At this particular point, you will have a magnetic field in this direction. Okay, here, look at this. Just draw an imaginary circle like this and make a tangent. So it will go in this direction. Understood? Next, here the current is going inside. Okay, the current is going inside. Therefore, the magnetic field will be in which direction? Again, the current is going inside. So the magnetic field will basically create a circle like this. And then at the tangent will be here, right? Okay. And here, look at this. Again, current going inside. So the magnetic field will behave like this in this direction. At this particular point, it's a tangent, right? So it will behave in this direction. So basically, you are only having two types of fields, due to which you have only two types of forces. Okay, one field in this direction, one field in this direction. Therefore, the resultant field will be in this direction. It is a vector addition of these two directions. See, we know that the current flowing in all the four wires is the same. That is something we know, right? So if the current is flowing in this, if the magnitude of current that is flowing in the wires is the same, then the magnetic field produced by them will also be the same magnitude. Okay, so all the four wires are producing magnetic fields having the same magnitude, but only thing that is changing is the direction. Okay, so there is two magnetic field lines in the upward direction. There are two magnetic fields in the downward direction. Okay, two fields in the upward direction, two fields in the downward direction. And what are they doing? They're adding up, right? They're adding up. So basically, if you assume, I'll show you how we do it. Okay, if you assume that you have a particle like this here. Okay, there is a magnetic field like this here. There is a magnetic field like this here. All you have to do is create an imaginary horizontal and vertical line and call this angle your theta. Okay, just call it theta. Now, basically, this field will become B cos theta B 2B. This is 2B and this is 2B, right? Twice the magnetic field. Okay, so this becomes 2B cos theta and this becomes 2B sin theta. And this is also theta. Okay, so this becomes 2B sin theta and this again becomes 2B cos theta. So a 2B sin theta in the upward direction and a 2B sin theta in the downward direction will cancel each other out, and you will be left with only one pair of magnetic field lines. The 2b cos theta and the 2b cos theta, which is 4b cos theta, will be in this direction. So you will only have horizontal components left. Therefore, the overall magnetic field will be in this direction. Understood? That's what they have done. Look at this. The overall magnetic field is in the P to this direction. Clear? Understood how I got the direction? You can get the direction by creating an imaginary circle and drawing a tangent. Okay, once you become more and more confident, you can see the circles in your mind and you can draw a tangent at that point. Okay, practice doing that. Understood? Yeah, see Akshay, the current is going inwards. This is a conductor with current going inwards. Put your thumb in this direction. Therefore, the magnetic field will be in this direction. Okay, it will be in the clockwise direction. Understood? So it's in the clockwise direction. Therefore, what will happen at this particular point? The direction will be here. At this particular point, the direction will be here. At this particular point, the direction will be here. At this particular point, the direction will be here. So the direction is governed by whom? It is governed by the spinning magnetic field, right? It's governed by the rotating magnetic field. Now, if you had the exact opposite of this one, if you had a dot, then what would happen? The magnetic field will basically travel like this. So you'll have a magnetic field here, 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 and here. Understood? This is how you draw a tangent. Clear? Fully clear now? Should I explain it further? Perfect. Very good. Two parallel wires. Is this the last page? Yeah. Two parallel wires X and Y carry equal currents out of the plane of paper. Both of them are coming out. Point P is at the same distance from X and Y. Which arrow currently shows the direction of the resultant magnetic field? Okay, let's place our thumb exactly like this. We have placed it. Now, we'll draw an imaginary circle like this. So, because the thumb is outwards, the direction of magnetic field at this point will be this direction. See, it is going in the anti-clockwise direction, right? It is anti-clockwise. Therefore, this field will be like this. Now, again, due to Y, what is happening? You are going to get a circle, imaginary circle like this. Wait, hold on. You're going to get an imaginary circle like this. And this field will also be in the anti-clockwise direction. So at this point, you will get a field like this. So both of them will have a resultant here. So only C is correct. Understood? How I got this? You understand? Okay, next. Exactly. Now, which arrow correctly shows the direction of the resultant field P? Arrow number C. Current in wire X is reversed and is now in the plane of is now into the plane of paper. What is the direction of the magnetic field at P after this change? Okay, let's actually do this. This is the point P. This is, oh no, I'm gonna draw it a little bit closer. This is what This is they said X, right? Okay. Yeah. And this is a dot. Okay. I have changed the direction of current. So basically, due to this one, uh, I'll have a current like this, magnetic field like this, but it will be in the clockwise direction. Now, due to this, I will have a current like, sorry, magnetic field like this, but in the anti-clockwise direction. Okay, so let's draw two tangents. Okay, for due to this, the tangent is like this, and due to this, the tangent is like this. So the resultant will be downwards. Understood? Clear. Next. A ring, a circular ring, carries a constant current. Point P is at the center of the ring. The magnetic field at P is directed into the edge. What is the direction of? The direction of the current in the ring. Wait, the magnetic field at P is directed into the page. So the magnetic field is going inwards. Okay. Yeah. So what's the direction of current in the ring? Again, you use the right hand rule. Okay. The magnetic field is going inwards. So the current has to go clockwise. Understood? So inwards means south pole. South pole means clockwise. Understood? Inwards. Yeah, exactly. Inwards and outwards. So basically, there is a section in India, in Indian physics, where we use this. And or simply dot 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 dot. This shows the field is going inwards. This shows the field is going outwards. Both of them are spaced uniformly, right? The two lines have uniform spaces between them. Therefore, this is a uniform inward field and this is a uniform outward field. Okay. What is the direction of current in the ring? We have found it. It is in the clockwise direction. And the direction of magnetic field at the point Q. Very easy. Just draw a circle like this. Okay. Better circle. You draw a circle like this. Now, the direction. Uh, Wait. No. Sorry. The current is going like this. No. The current is, since the current is glowing like this, therefore, the magnetic field is inwards, right? So if it is inwards, then it will form a loop like this. Okay, see, if this is inwards, then you will have the magnetic field like this. If this is the loop, then the magnetic field will be like this. It is going inside, and at the point Q, it is coming outside. Magnetic field is coming out, going in, coming out, going in, coming out, going in. Understood? That's what's happening here. So the Q will have a magnetic field outside. It will be coming outside towards you. Then only no, it can go inside also. Understood? So the magnetic field at this point will be outside and it will be actually trying to go in like this. Okay, outside, inside, like this. And the shape is really bad. I can show you a shape like this. See, if this is the point P and this is the point Q, then the magnetic field will come like this and go like this. It is going inside and it is coming outside. So the loop, the magnetic field is going inside, outside it's coming outside. Therefore, the Q will experience what? It will experience a magnetic field in the outward direction. Okay. It is very difficult to show these in two dimensions, but I hope you understood that. Okay. Okay. Next. Current in the ring and the magnetic field. Wait, what does it mean? What is this? Oh, they have given us options. It's an MCQ based question. Okay, so it will be clockwise and out of the page. Okay, it will be a clockwise current and it will be a clockwise current and the magnetic field at point Q will be out of the page. Understood how we find these things? Okay, fine. So I think we have officially finished this chapter. Okay. Motion in electrical fields. What is this? Oh, this is the last page. Next page. Next question. This thing. Okay. So wait. Yeah, we have finished the second part. Officially, we have finished the second part. So, students, we have finished the second part of this chapter, uh, electric and magnetic fields. Okay. Now we are going to start with the next section, that is motion in electromagnetic fields. How does motion in electromagnetic fields affects the objects that are going through them? Okay, so in the next video we will continue with the next chapter. So I hope you understood this video. I hope you like my explanations, and if you do, please do like, share and subscribe, and I'll meet you in the next class. Bye.